Extension energy transfers. Hooke's law. If you draw a force extension graph and the relationship for the spring is elastic, it's directly proportional, so the force that you've applied is directly proportional to the extension, you receive this straight line, the top one. Okay, it's steeper than the other. Another different spring, so not the same type of spring, but a different type of spring, would have a different relationship, still directly proportional, okay, still a straight line through 0, 0, but it's not quite as steep as the other. Alright? The relationship for both, we said, was force is directly proportional to extension. If we make that an equation, we change the proportionality to equals k. That's true of any equation in maths, so generally it's equal k. But in this one, we're going to keep k as k, and k is the spring constant. Okay? So the spring constant k, if we use the graph, force extension, if I rearrange this equation, F equals kx for k, k is equal to F over x. Okay? This equation, F equals kx, is another one you have to remember. You will not be given F equals kx in your exam. So you have to remember the Hooke's law equation, F equals kx. K is the spring constant. If I rearrange the equation, I get k equals F over x. If I look at the graph, F divided by x is the y divided by the x-axis. Okay? Or changing y over changing x, which is the gradient. So the spring constant is the gradient of a force extension graph. Okay? If you want to determine the spring constant for this spring, you can see already without doing the calculation that it's steeper. A steeper gradient is a greater, larger value for the gradient. That means it has a larger spring constant. Okay? This one is more shallow. Okay? It's not as steep. Its gradient is less. Its spring constant is lower. What that means is spring constant K is stiffness. Okay? If you have a large spring constant, that means it's going to require a large force for a specific extension. Okay? If you have to apply a greater force to extend a spring, that's a very stiff spring. Okay? It's going to take a lot more force to extend. Whereas this one, with a lower K, a lower spring constant, so therefore a lower gradient, it won't require as much force to extend. So the definition of spring constant is the force required to stretch a spring 1 meter. It's a constant value, the same as density. How much mass per volume? Okay? Same as specific heat capacity. How much energy per kilogram per degree Celsius? Okay? Spring constant is the force required to extend or stretch or even compress. Okay? So be aware, this graph is that you could also do this for compression, not just extension. So you could be stretching the spring, or you could be compressing it. You could be stretching it vertically by hanging masses on the bottom, or you could be doing it horizontally. The same rules apply. If I put a spring horizontally on a table, on a desk, and I apply a force and I start pulling it, it will still stretch the same way. Or if I compress it, okay, or an object that can compress. Alright? So Hooke's law, F equals kx, the spring constant is stiffness, so a greater spring constant is a stiffer spring. More force is required to stretch it 1 meter. Alright? You don't have to stretch it 1 meter, you can put the values in and use the equation to find extension or force. You have to be very careful, the units of K are Newton per meter. Okay? They may in the exam give you the extension in centimeters or in millimeters. You have to convert those. The force should be in newtons. Could be in millinewtons, could be in kilonewtons. You have to convert them. Alright, so be careful. The spring constant should be in Newton per meter, not centimeter, okay, per meter. Now, same graph, force extension. But this time we're not looking at how much does the spring extend. I want to know if I do extend a spring or compress an object, how much energy have I stored inside it? Okay? Because if I pulled a spring and stretched it now, and I let go, you know that the spring would fly off and I would have given it kinetic energy. Okay? But how can I give it kinetic energy if there wasn't an energy before? There must be some energy that I gave to the spring in order to transfer that to kinetic energy. So the energy stored inside a spring, if I stretch it or if I compress the object, is elastic energy or elastic potential energy. Okay? So energy stored inside a stretched spring is elastic potential energy. Okay? How can I calculate the elastic potential energy stored inside a spring? If I go back to the force extension graph, it's directly proportional. Goes through the origin 0, 0, it's a straight line. If I want to calculate the energy stored, I have to find the area underneath the force extension graph. Okay? So the gradient of a force extension tells you the spring constant. The area underneath the force extension tells you the energy stored inside the spring. If this is the graph, and you're always going to get a straight line directly proportional for force extension on a spring, if it's elastic, and it hasn't gone past that point, okay, then the area underneath is a triangle. And if you want to find the area underneath the graph that's a triangle, you have to do the base, which is the x, times the force, which is the height, but then you have to halve it. Okay? So the area underneath the graph, which is a straight line to 0, 0, but it's an increasing line, it's a triangle, you have to do half force times x. Okay? So the energy stored inside a spring is half Fx. Now, because I have an equation for Hooke's law, F equals Kx, and I just said that the energy stored inside the spring is equal to half Fx. That half, remember, comes from the fact that it's a triangle. I have to halve it if I want to find the area underneath the line. Okay? But I know an equation for F. So for example, in the exam, they could say calculate the energy stored in the spring. Here is the extension, and here's the spring constant, but they didn't give me a force. Then there must be something I can do. So if I swap this F for Kx, E becomes 1/2 Kx times x. So therefore, energy or elastic energy stored inside the spring is 1/2 Kx squared. Okay? This equation will be given to you. You don't have to remember this equation, it will be given to you. What you do have to remember, if you're not given the spring constant, there is a chance, first of all, they may give you a graph and say, please find the energy stored inside the spring. You just have to find the area from the values you're given. You either do the triangle, just do the base times the height. They may say, find the energy stored inside the spring at an extension of this. So I only have to go this far and find this triangle, or at a force of this. Only the triangle where the force is this value, not the whole graph. You have to be very careful that if they say, find how much energy would be stored if I applied a force of 10 newtons, and the whole graph went up to 50 newtons, you're not finding the area under the whole graph. Okay? You could be asked to count the squares. Alright, they may ask you to count squares, or that you may just want to count the squares. It's up to you. You either do the base times the height and halve it, it gives you half Fx. So you can, if you're given the force, find the energy stored without the spring constant, and vice versa. If you're given the spring constant, then it's half Kx squared. Only the x is squared. This is the same as kinetic energy. Half mv squared. Only the v is squared. If you want to rearrange this for k, then k equals 2 times the kinetic energy divided by x squared. And if you want to rearrange this to find extension, extension equals 2 times the energy divided by the spring constant, all square root. Exactly the same as kinetic energy. Okay? One more thing, and it's a question that can come up quite often, and a question that most people will get wrong. If I'm finding the energy stored in a spring, the energy stored in my spring is due to stretching or compressing. Now in 15a we said if you want to stretch or compress an object, you have to apply a force. If energy is stored because of a force, then I have to do work on the spring. Yeah? Energy transferred by a force is work done, in any case, in any context. So if I stretch a spring and I apply a force on the spring, I've done work on the spring. So the work done on the spring, we know work done is force times distance. But this does not apply to spring. You cannot use the equation work done on a spring is force times distance. The equation for energy stored is 1/2 force times extension. Extension is the same as the distance. If I stretch a spring 20 centimeters from its original place, then the distance that the spring moves, if you want, is 20 centimeters, which is its extension. So how come if work done is force times distance, And this equation is half force times distance. Why is there a half in this and not in this? What's the difference between general work done, force times distance, and doing work on a spring? If you want to do work on an object by applying a force, so I draw a force and distance graph. Okay, for example, if the brakes of a car are doing work on the car to slow it down, so the brakes apply a force and it travels a distance. The force from the brakes, let's say, is 200 newtons, and the distance travelled by the car before it stops is 20 meters, then that force will be doing work on the car the whole time to there. In this case, in every general case where you use work done equals force times distance, the force is constant. You apply a force on an object and you apply that force over a specific distance. This is what the graph looks like. If I want to find that energy work done from this, I'll find the area underneath. It would just be a rectangle or a square. It would be force times the distance. But it's not the same for a spring. Okay? In the equation, you have the half in front of the force times the extension. Alright? The explanation for why can I not use work done equals force times distance for springs, because the force on a spring as you're doing the work is not constant. Okay? The force changes. Every time I extend the spring, I have to apply more force. Yeah? I can't just apply one force and its extension will go down, and then a little bit later it will go down again itself for the same force without adding anything else. It doesn't work like that. If I apply a force on an object in this context for work done, then that force can happen over a specific distance. The force is constant. But if I want to do work done on a spring, it has to be half the force times the distance because it's a triangle. And the reason it's a triangle is because as the extension changes, I'm adding more force. The force is not constant. Okay? So the explanation for why can I not use work done equals force times distance, because the force on a spring is not constant. In order to do work on a spring, you must keep changing the force. Okay? Done.